Okay, this is lesson 6. This is the first lesson that there's going to be 2 videos. So this first one we'll call it part A, and it deals with Kirchhoff's rules. It's more of a lecture, an explanation of how to solve the problem. The second part will be on the voltage divider, which is at the end, and it'll be a short one. I just want to say a little bit about that. So in this lesson, we're going to look at how to apply Kirchhoff's rules. What you had done in some of the previous lessons, when you had one resistor or one battery and several resistors, you could add the resistors in series and parallel, get an equivalent resistance, and then you could work backwards as needed to solve for currents and voltages. Well, if you notice this circuit, this is the one that you have on page 37. I don't have all the markings on it yet, but I've just drawn the basic circuit. You notice that there are several branches. This is actually 3 branches, but the important thing is that there are batteries in each of the 3 branches, which is not what you had in the previous circuits. So you can't really add resistors in series and parallel because you have the batteries in between. So you have to use another method. And what we're going to do is use Kirchhoff's rules. You were introduced to those at the end of lesson 3, and so we're going to apply those. Now in lesson 3 you didn't really know why you were doing that, but like now we're going to use those. So before we actually apply those, I want to go through the process. Now what's interesting is that we have 3 branches and we don't know what direction the current is going. So when we pick a direction, it says to choose a direction for the currents. You have your choice of picking a direction. What you're going to find out at the end is if you happen to choose the direction the current is actually going, you will get a positive value for that current. If the current's going the other direction, then you will end up with a negative. So what I'm going to do is a combination of what you have on page 37 and the instructions on page 38, and then we're going to end up with the equations that we need on page 39. So it might help if you take the pages out of your book and kind of lay them out side by side so you can kind of go from page to page. So the first thing is pick a direction for the current. Well, when we drew the picture, we did pick a direction, so I'm going to choose the same directions, obviously, that are in on page 37. So we're going to look at this left branch. We have from here around to here. This is a series, and we know that the current is the same at all points in a series. Now, when it gets to the junction, then current may either join or split somehow. So we don't know quite how these are related yet. So we're going to choose current here, and in the lab it has a picture, kind of a fat arrow. I usually don't draw very fat arrows, but I'll put an arrow there, and we're going to label this as I1. Now, something that you want to make sure that you don't make the mistake of, this I1 is close to this R1. So you might say, well, I have I1 for R1, I2 for R2, and so on. That's not the case. This whole left branch has the current I1. So the I's are independent of the resistors. Now, in the middle branch, we chose upward again, just because you have to pick a direction, so that's what we chose. And we're going to call this I2. And then in our right branch, we're going to label choose to the right. So this is going to be I3. And from this junction up at the top all the way around to the junction at the bottom is I3. Okay, so that's the first step. Now, one of the things you're going to find out is you have lots of choices. And you could probably have everybody in the class, there's 9 people in the class, everybody in the class could probably choose things differently, but you still end up with the same results. And that's kind of amazing, I guess. Okay, so we've chosen the currents. The next step, in step 2, it says to choose okay, we did that. Step 2 is to label the resistors with plus and minus. So what we're going to do is if the current is going into the resistor, that side is a plus. So I might over here put in plus, out, minus. So I'm going to start back here at this junction. If the current is going up on this part, it has to be going to the left here. It's starting here, going all the way around there. So I'm going to start here, and we're going to say in the plus, out the minus. Here, in the plus, out the minus. And then we're up to here. Notice I'm not doing the batteries yet. That's a separate issue. I'm going to go do all the resistors first. So here the current is going from the bottom to the top, so I'm going to put in the plus, out the minus. Up here the current is going around to the right, so in the plus, out the minus, in the plus, out the minus, in the plus, out the minus. Now, at this point, you don't know why we're labeling that, but we'll see that in just a little bit. Okay. Then the next step, let's see, something else that's actually down in step 4, potential difference for batteries and power supplies. The long side of the battery is the plus side. It does not matter which direction the current is going through the battery. So for the long side, we're going to put a plus for the long side, a minus for the short. And we go up here, this is the short side, so that's minus, that's plus. We have a battery here in the middle, the long side is plus, the short is minus. We have one more over here, the long is plus and the short side is minus. Okay. So we've chosen our currents, or we've picked a direction for the current, which we don't know whether it's right or not, but that's okay. And we've labeled the resistors with pluses and minuses based on the direction that we chose for the currents. We have labeled the pluses and minuses for the batteries. So the next step is to apply Kirchhoff's rules. There were 2 of them. One of them is that the sum of the voltages around a loop is 0. So if we look at this, we can see that we actually have 3 possible loops. We have a left loop, we have a right loop, and we have an outside loop. And with each loop, we can pick one of 2 directions. We can either go clockwise or counterclockwise. Now, where we're headed with all of this is to solve for the currents. So we have 3 unknowns, and from the math point of view, if you have 3 unknowns, you must have 3 equations to solve for those 3 unknowns. Not only must you have 3 equations, but they must be what's called linearly independent. And you may or may not have heard about that. If you have, it probably was in algebra, possibly some number of years ago. But if equations are linearly independent, you cannot add 2 of them and get the third one. One of them is not a multiple of another one. And it seems like there was some other condition, but I don't remember exactly. But here, what will happen if you do a left loop, an equation for a left loop, a right loop, and an outside loop, if you add the left loop and the right loop, you can get the outside loop. So the point is that of those three loops, there's only two equations that are linearly independent. And again, you have choices. It doesn't matter which two loops you pick, and it doesn't matter which direction you go around the loop. So again, you have to make a choice. Now, what we decided to do is, let's see, I am going to write an equation for the left loop and another one for the right loop. Now, something else you should do is to pick a spot to start and put a dot or a star or something so that you know when you have gone completely around the loop. You don't want to stop before you've gone completely around, but you don't want to go around and keep going. So we picked a spot on the left loop, and I think I'm going to use some different color. I decided I'm going to start here. I'm going to put an S for start. Now, when I start here, I have to go some direction. So I decided I'm going to go counterclockwise. So I will put like a little arrow there to show which direction I'm going. Okay? I'm also over here going to start at this point, so I'm going to go ahead and label that. And I think I went clockwise on this one. Now, something that you can do if you want to is you can make the same choices all the time. So I typically take up on the left, up in the middle, and to the right on the right one for the directions of the current. I typically pick a spot up here, go counterclockwise, pick a spot up here, go clockwise, left loop and right loop. Now, as I said, you can go either direction. You can pick any two of the left, right, or outside loop. You can pick any two of those that you want to. And you don't have to do the same thing for each problem. But I have found that if I pick a sort of general way of doing the problem and do all the problems the same way, then I don't have to kind of think about and make a decision. It's like I do it the same way all the time. Okay, so now we're going to write an equation for the left loop, and this is what you should be writing on page 39 in step 1. Well, actually, let's do the left loop. That's step 2. Write a loop equation for the left-hand loop. Okay, so if I start here, I'm going to go around here. Now, we're going to look at voltages. We know that the voltage for a resistor is current times resistance. So if we start here and go through this resistor, the current for that resistor, okay, I need to put left. And I'm going to put counterclockwise. So I'm going to abbreviate it CCW. Okay, so I have I1, R1. I1, R1. Then we have to decide, is it plus or is it minus? And that's why we have these things labeled. So the rule is, for resistors and for batteries, the sign is the sign of the side that you leave. So you could even make that into a song or something. Okay, so if I go this direction, it doesn't matter that the current is going up. I am thinking about walking around this. It's similar to walking beside a river. The water's flowing one direction, And you don't have to walk beside the river the same direction the water's flowing. You can walk upstream if you want. So that's kind of what we're doing here, is thinking about walking upstream. So I go through here, I leave the plus side, so I'm going to actually put a plus to indicate that we thought about it and decided that it's a plus. Here we're going through the battery. The voltage for battery is just the voltage, so we have V2. When we go this direction, we're leaving the plus side, so this is a plus. We come to another resistor, so that is the same I1. In this left branch, the current is I1 all the way around that branch. So we have I1, R2, and we're leaving the plus side, so this is plus. Now, at the junction, we turn and go up the middle. So we go up here. Now this is I2. So we have I2, R3, and we're leaving the negative side. Then we get to this battery, and this is V3. We are leaving the negative side, so that's minus. We get to this top junction. Now, we have to remember that we started over here on the left, so we have to turn left to get back over to our starting point. We don't want to go that way. We have to get back to here. So we turn and go left, and this is V1, so we have V1, and we're leaving the minus side, so this is a minus, and we're back to where we started, so this sum is equal to 0. So we have our, in step 2, the equation for the left loop. Okay, step 1 was the right loop. I'm not sure why I did the right one first, but so the right loop, and we're going to go clockwise. So we're going to start here. We go through this battery, that's V4. We leave the plus side, so this is a plus. We come to this resistor. Now, the current in this right-hand branch is I3. So we have I3, R6. We leave the negative side, so we put a minus. We get here, we're going through R5. It's still I3 times R5. We leave the negative side, so we have a minus. We get to this junction, and since we've decided to do the right loop, now we need to go up through the middle. So we go up through the middle. This is I2 times R3. I2 times R3. We're leaving the minus side, so this is a minus. We get through the battery there. That's V3. We're leaving the minus side, so we have minus. We get to the junction, and we know that we started over here, so we have to turn right to get back to our starting point. So we're back on the current that's I3. So we have I3, we leave the minus side, oh, have to have times R4. We're leaving the minus side, so we have a minus. We're back to our starting point, so that's 0. You might notice that the terms for this middle branch, since in both of them we went from bottom to top, those terms should be the same. So this matches this and this matches this. Okay, so we have 2 equations, but now we need a third equation, because if we were to do the outside loop, I think if we were to add these or subtract these, I don't remember exactly which one it is, you would get that third equation, that third loop. So it's not a linearly independent equation, so we cannot use it to help us solve our equations. So the other thing that we use is the junction equation. So I think I'll just do that in red up here. So we have the sum of the currents is equal to 0. Now, what you did in lesson 3 was you wrote it a little bit differently. You wrote it as current in equals current out. Well, it's easier to have it equal to 0, and then we need to indicate Usually we have the in currents as plus and the out currents as minus. Okay? So if we look at the junction, and I decided to do the top junction, I'll call this J1. So at J1, the currents going into the junction, so the arrows that are pointing toward it are I1 and I2. So we have I1 plus I2. I3 is leaving the junction, so that's minus I3, and then that has to equal 0. So you might say, well, we have a junction at the bottom. So why don't we use a junction equation here and a junction equation here? Well, if you look at this one is coming in. It would be a plus I3. These two are leaving. That would be minus I1 minus I2 equals 0. And that's exactly this equation except multiplied by a minus. So it does not give you another equation that you can actually use. Okay, so we have these three equations and we need to solve simultaneously. So you look at that and say, oh my, that looks very complicated. Well, the first thing that you need to do, the next thing you need to do, is to go through and put in the resistor values and the voltage values. And those are actually written on page 37. I generally always label these with R's and V's, and then I put in the numbers after I have these equations. So I'm not going to write out some of the intermediate algebra. I strongly recommend that you do. And if you do that, let's see. In this first equation, if you put in the values for the resistors, and this is one place where I recommend that you do not put units. Most of the time, I'm always complaining about you have to put units with your numbers. But this is one place that it's perfectly acceptable not to put the units. So if you go through and put in the values for the resistors and the voltages, I'm going to just show you the end result. And you should probably do that, I guess in step 4 would be where you would do that. So we're going to end up with 10 I1 minus 5 I2. Now, in this first equation, there are no I3s, but so that you make sure you get your numbers entered correctly into whatever you use to solve this with, I always go ahead and include the ones that don't exist. So I would put 0 I3, and that equals 10. Okay, so that's equation 1. I might label this with a 1 and put a 1 here. So if I do equation 2, then I'm going to get 0 I1 minus 5 I2 minus 32 I3, and that equals 2. Then my third equation basically looks fine as it is. So I'll just put that. Have I1 plus I2 minus I3 equals 0. So these are the three equations for which you have to solve simultaneously. Now, I highly recommend that you do not try solving them algebraically longhand on paper. I've done that before, and it's very easy to make all kinds of arithmetic mistakes. So, I think in the lesson I tell you if you have a TI-85 calculator, and it has to be a TI-85 for it to be simple enough to do. You can start with the Simult, S-I-M-U-L-T button, and you enter the numbers kind of like it shows. Now, I realize that a lot of you may not have a TI-85, so I found a website, actually one of my students found the website, and it works very nicely, and I have the link to it in the lesson. But in this website, it's called Linear Solver, and it will have a box, and you simply enter the 3 equations, you just type them in, and I tell you in there, I would recommend that you use X, Y, and Z instead of I1, I2, and I3. And you enter those, and then you push solve or something like that, and it will solve these simultaneously for you. And I did check this problem, and it does work. So I'll go ahead and give you the values here. The reason I need to show you the values, normally I wouldn't, I just let you do it, but I need to show you these for the next part that we're going to do. So we get I1 is 0.679 amps, so you should go ahead and put the units there. I2 is minus 0.642 amps, and I3 is 0.038 amps. Okay? So you should make sure that you can go through and do all of this and that you end up with those values. So when you have done this, then you have solved for the 3 currents. Notice, and we'll look at this a little bit later, notice that I1 is positive, so I1 actually goes the way we have it. I2 is negative, so instead of going from bottom to top, it goes from top to bottom. It goes the other direction. I3 is a positive number, so it goes the way that we have it there. Okay, so that should take you to the bottom of page 39. Okay, now we need to look at power. And one of the previous lessons, you had derived some equations for power for a resistor and a power for a battery. So we're going to look at those because there's a description there as to what you actually do, but sometimes unless you sort of already know what you're supposed to be doing, it isn't exactly that clear. I think what I'm going to do, I was going to try to write all the stuff over here, but there's really not enough room. So I'm going to leave my circuit there, but I'm going to erase these equations, and I'm going to write the current values down here, and then we're going to look at the tables for the power. So we're going to put I1 is 0.679, I2 is minus 0.642, and I3 is 0.038 amps. Okay, so this is a combination of following the instructions and filling out the tables kind of at the same time. So in the table for the resistors, it has the resistors numbered 1 through 6. So I'm going to do this. 3, 4. I'm not going to put the brackets in there. I'll just do it where you can tell what's what. So then the next column is to record the values of the resistors. So this is R. So 8 and I'm going to try to keep these in line. 8, 2, 5, 10, 2, and 20. Okay? Now, this table isn't really that complicated. So I'm not sure I don't think I'm going to put the rest of the values there. I'll just tell you. But this is for the resistors, and power for a resistor is minus I squared R. You didn't use the minus sign before, but the minus tells you that the resistors are using energy. They're converting electrical energy into heat energy. So for a resistor, we just always have the minus. So there's the next column is current. So I'll just put it up here, and then this is power. So for the current, you need to go through each resistor. So for R1, the current is I1, so it would be 0.679. Now, for the resistors, it doesn't matter whether the current is negative or not, because you square the negative. And if you're doing this on your calculator, you probably need to make sure that you have this minus in parentheses, or it's not going to square this negative, and then it's going to confuse the issue. So you'll go through, write the currents here, and then the current squared times R will give you the power. And so that will fill out that table. And then you're supposed to add those together, and I will go ahead and put that value down here. It's minus 6.717, and these are watts. Okay, now the confusing part comes with the batteries. You might say, well, why is it confusing? Because power is current times voltage. Well, we're going to see that in some of these, the current goes through the battery and comes out the positive side, which is normal. Some of them, the current goes what I call backwards through the battery, and that's a separate issue. So we're going to start with our voltages, 1, 2, 3, and 4, those batteries. The values are 12, 8, 6, and 4. And then it tells you somewhere in there, well, it tells you to record the absolute value of the current. So whether it's plus or minus, it doesn't matter. In this column, you record the absolute value. So I'm going to do that. This is 679, 679, 642, and 038. Okay? Then the next step is to calculate power by our equation, current times voltage. So you just multiply the current times the voltage, and I seem to be going uphill with this, but this is okay. So this one is 8.148. This is 5.432, 3.852, and 0.152. Now, if you were to add those, you can see right away you're going to have 8 and 5 is 13, 14, 15, 16 or so watts, which doesn't match this value at all. Well, the problem is we have not considered the direction the current is going through each of the batteries. In one of the previous lessons, it talked about when current is going through a battery, or when current leaves a battery, the chemical energy is being converted to electrical energy. Now, if the current goes backwards through the battery, then the opposite is happening. We have electrical converted to chemical. So we have to figure out what's going on in these batteries. So I'm going to use my orange marker. So what we do is look at each battery. Is the current going through it and coming out the positive side? So I1 is going this direction, and I1 is positive. So the current really is going that direction. So I'm going to label this with a big arrow out here beside the battery. Notice that when I found I2 was negative, I did not go back and change the direction of my arrow. You don't want to do that, or then you have to go through the whole problem all over again. You leave them the way that you had them to begin with. So if the current goes through the battery coming out the positive side, then that is a positive value. So for I1, we have a positive value, so I'm going to label this as positive. Then we go to battery 2. So the current is going up here, which means it had to start from here going this direction. So the current is going backwards through this battery. So it is leaving the negative side. Since it's leaving the negative side, now notice that that's not a negative I1. So you don't want to say just because I1 is positive that all these things are positive with I1. That's not right. So you see which direction the current is actually going through the battery. It's going out the negative side, so then the power for this one is negative, and that's 2. So we'll put a negative sign there. Okay, then we go to battery 3. We found that I2 is negative, so I2 is going the other direction. It's really going this direction, which is coming out the positive side. So our R3 power is positive. So we put positive there. Then we go to battery 4. I3 is positive, so we have I3 really going the way we have it, so it comes around here and goes this direction. So it's actually going through the battery, coming out the positive side, so then we have a positive here. Okay? So most of the rest of filling out the tables it's not really all that complicated. But the pluses and minuses for the batteries, not for the batteries, but for the way the current is actually going through the battery, you have to figure that out. And I normally always put those arrows out beside the batteries, not on them, but beside them. And then that tells you whether this power number is positive or negative. You don't get it from the minuses here. There might be a way to do that, but the way I explained it, you really need to figure out which way the current is actually going through the battery. That gives you the sign for the power. And then, when you use those signs and add this up, you get 6.720 watts. And notice that that is extremely close to what we had here. So what we're saying is the net result of the batteries, the current, or the chemical energy going to electrical energy, the net of that is the same as the net of the electrical going to heat in the resistors. The other thing that I would do over here is, if this is a positive, this tells me that we have chemical going to electrical. If it's negative, then we have electrical going to chemical. These are both positive, so these are chemical to electrical. Now, where this minus is useful in real life is when your car battery dies and you have a charger, or you take it somewhere and have it charged, or well, I guess if you get a new one, then you don't have to worry about it. But if you're trying to get that battery recharged, then you are forcing current through it backwards from what it normally operates at. And when you do that, then the electrical energy is being converted to chemical. Once the battery gets charged, then it is available to use normally, so then the chemical would go to electrical. Okay. Let's see, I think I'm at the end of my notes here. Okay, I mostly wanted to go through this explanation because if you're trying to do it by just reading, it is kind of difficult to make sure that you've got all the details there. So if you go through the process and then make sure that you do the process to figure out the pluses and minuses on the power, then I think you should be fine. So that should take care of the example. And then there's a problem that's called application, where you do the same thing. And then I have another problem in the homework, I think. Oh, I can look that later. One other comment on page 43, Kirchhoff's voltage rule for a single loop. At first you might think, oh, how do I do a single loop? Well, it's really fairly simple. You just pick a direction for the current. There's only one current, and you have a single loop equation. You're solving for one current, and then it's pretty easy. It's just one equation, one unknown. Well, if you get confused on any of this, it's certainly fine to email me or call me.